Comes up and then I will introduce you. Okay. There we go. All right. So welcome everyone. It is my absolute pleasure to introduce today's seminar speaker, Professor Hyunjung Chung. I've introduced you before, so I should be able to do this. I just want to tell you a little bit about Professor Chung's background, and he is an associate professor of chemical and materials engineering at the University of Alberta, and he's had a very interesting and multidisciplinary career path. He received his BSc from KAIST in 2000, and then he did his PhD at the University of Pennsylvania in 2005, and that was in polymer physics. So he studied phase behavior of polymer blends and nanoparticle composites and all sorts of like interesting, composites like that. And then he went on to be a senior engineer at Samsung Display for several years, and he worked on developing zinc oxide-based thin film transistors for large-sized OLED TVs. So extremely, practical, commercialized type work. And in 2009, decided to come back to academia, which is our gain, certainly, and did a postdoc at the University of Illinois with Professor John Rogers, who was there at the time, where he worked on biosensors and flexible electronics. He moved into his own research lab in the University of Alberta, and he has this now multidisciplinary research group where he focuses on studying stretchable soft materials, gels, elastomers, textiles, devices, basically, pulling from this really diverse background. And I really wanted to invite Professor Chung today for this CREATE network because I think everyone will really appreciate his approach to research, which is an engineering approach, but tries to solve problems that are important and problems that are relevant to people, to actually, really makes that linkage, which is something we really are focusing on in this CREATE network, and we really built our network on those principles. So Professor Chung has published highly influential papers, highly cited papers, and he holds 12 patents with a possible another one coming, I'm told. And welcome, and thank you so much for taking the time to talk with us today. You can share your slides, and looking forward to your talk.
Okay, I shouldn't do that. Just give me a second. Sorry about the delay. Okay, now it'll work. Thank you so much, Tricia. It was a great honor to be introduced, and so nice. Thank you so much, and thank you for SMAP and Professor Rong for inviting me in this opportunity. And this is a beautiful Kananaski. And today's talk is going to be about the elastomeric materials and embedded sensors for medical devices and smart prosthetics applications. So I am going to introduce some medical engineering, biomedical engineering pieces of my work, my group's work. So elastomers is rubber, basically. Any material that is elastic, stretchable, but resilient, that is called rubber with the toughness. And nothing is running without rubber is a statement, and that is definitely not overstated. And then here is my background, my academic background is in polymer physics. So I see rubber as a polymer network, which is a polymer chains that is held together by covalent bonding or some sort of cross-linking. So that is my viewpoint of this whole system, and this network is actually extending to the macroscopic objects like textiles. So you will see it very soon. Elastomers are also occurring a lot in the modern examples of technology like substrate materials of the stretchable bioelectronics that can be worn on the organs and skin, or electronic skin itself. So elastomers are now embedding electrical active devices in it, and then they are evolving it to some advanced form. And also in the sensing and actuation, magnetorheological elastomers and the dielectric elastomers, that they have been around for like decades, and then they are now evolving into the soft robotics form. So these technologies also coming, and this is definitely one of the most promising applications for the advanced surgery application. So this is hot research area in the materials engineering, and also gels. Basically, so gels are often misunderstood in terms that people are looking at the application in a quite a limited manner, because the gels that you see in the market are predominantly soft, brittle, and very non-functional. But gels, by definition, is basically elastomers swollen by the solvent. So if your solvent is swelling your polymer, and if that resulting polymer is making resilient elastomeric behavior, then we call it tough gel. Specifically tough gel. And tough, well, this is brittle gel, of course, but tough gels has been around in nature, including our own skin. And then how tough it can be. It can be tougher than steel as well with the reinforcement. So hydrogels can cover a wide range of mechanical properties. And textiles are also very interesting engineering material, because this is somewhat like polymer networks. The structure, even if the yarn itself may not be stretchable, if you knead the yarn, then they can make a stretchable material just like our own clothings. And this aspect has been captured really nicely by Professor Tricia Carmichael's papers on wearable LEDs and whatnot. So you definitely want to see those exciting papers. And then also these mechanical properties of these textiles, which has been around for thousands of years in the application technological perspective, is revisited nowadays. The APS American Physical Society meeting is really the physicists are actually looking at these material, how they can make a specific mechanical property in a very academic terms nowadays. It's actually interesting. So our research is based on the elastomers and gels, and we also employ textiles to pursue many different applications. And today I'm going to focus on these biomedical applications and for rehabilitations. So that is what I'm going to focus today. Today's talk is going to be in 4 pieces. Actually, a good half of the whole talk will be about our new result about the self-regulating Moog aorta tube. And then we are going to talk, I'm going to talk about briefly about the smart jaw prosthetics, and then the EMG patch, and then electronic skin for the sensitivity. So yeah, this is the plan for today's talk, and the first half will be on this Moog aorta. So this is the motivation, ex situ heart perfusion. So this is heart. This is how the heart is delivered, and basically heart is delivered in the ischemic state, which means that instead of dying quickly, heart is dying slowly, and it is practically said that it's probably giving 4 hours for the delivery, which is not ideal for, especially for the huge country like us, Canada. So researchers, the surgeons and biomedical researchers are working on normothermic ex situ heart perfusion, which is this. This is great. It looks like heart is living, but this is somewhat deceiving. The reason that I'm saying it is that yes, heart can beat, but heart is autonomous organ. If you put the glucose and oxygen, it will strike its own beating mechanism. The problem with this equipment right now is that the blood is not really circulating here, so the heart